record. Yeah, okay, well, we're recording now. And once again, I think it's going to record into the cloud. So that's more problems for me tomorrow. But anyway, never mind. Okay, so we're very pleased to welcome Sergei, who's going to talk about, well, why don't you tell us what you're going to talk about?
Okay, let me try to share the screen. Let's see if this works. Can you see it?
Yeah.
Yes.
Okie dokie. Yeah, so thank you. What I'm going to talk about is two papers, one with Ciprian Manolescu, who is here. So this was written in 2019, and a slightly more recent paper with several collaborators and colleagues, Dupay, Porsche and Xie, Sonyuk Park, Nikita Sepenka, and Hiraku Nakajima. So this was written several months ago. And in this talk, I'll try to address two problems, which are roughly speaking accommodated in those two papers, but there is a huge overlap and many interconnections between them. So I think it may be unfair to divide two problems into these two papers. But more importantly, it's part of a bigger ongoing program or story, and many chapters in the story are not written yet. So therefore, I appreciate questions, comments, thoughts, all kinds of suggestions. And also, I imagine that the background may vary in the audience. So if there is something unfamiliar or unclear, feel free to interrupt me, ask questions anytime. I don't plan to rush. So if there is something confusing or unclear, feel free to just speak up. Okay, I'll start with motivation, and this talk will be about knots and three manifolds. So the title, official title was logarithmic invariants of knots and Q-series invariants of three manifolds. And in the territory and the land of knots, one question that naturally came up and was asked by many people, notably by Michael Atee, is why invariants of knots typically have integer coefficients. So you probably know about knot invariants such as Alexander polynomial, Jones polynomial, Humphrey polynomial, and there are many versions of these invariants. They're colored versions. For example, Humphrey PT can be colored, and there are various invariants associated to other Lie algebras and groups, Cartan types that come from quantum groups, and all of them, no matter how hard or complicated invariant you try to imagine, it comes out with integer coefficients. So one question, natural question that was often asked in 80s and 90s when these invariants were developed and studied is why these coefficients would be integer. And throughout 90s, by late 90s, two answers naturally emerged. One in math and one in physics and parallel developments. And in both cases, it was realized that the integer coefficients that we see in familiar knot invariants such as Humphrey PT polynomial, Jones polynomial, and many others are graded Tolle characteristics of some doubly graded homology theories. So if there exists an invariant of knot, which is not a number, but or polynomial or function, but rather homology theory, then the mechanism to produce polynomial is to sum with weight -1 to the I with respect to one grading, q to the j, where j is another grading, and in that way you recover an entity which manifestly has integer coefficients. So in math, these homology theories were developed by Khovanov, Osvald-Szabo, Khovanov-Rozansky, and many others. And in the world of physics, these homology groups usually go by names of BPS states, or more precisely spaces of BPS states. and they were studied actively in late 90s by Kumar and Waffa and many of his collaborators. Naturally, these two developments actually coincide. In other words, they are not just parallel developments. What physicists call spaces of BPS states are the same as this homological invariance of knots and vice versa. So if you know one, you can just translate it into the other. But in any case, the title of my talk is Knots and Three Manifolds, or something and something about knots and three manifolds. And we know that topology of three manifolds is closely related to topology of knots. More on this later. So naturally, one might think that there should be analogous story, which goes by the name categorification for three manifolds, namely the polynomial invariants I just mentioned, the Color-Jones, Humphrey, and Alexander polynomial are examples of quantum group invariants. And you can imagine that if you try to study analogous quantum group invariants of three manifolds, there should be analogous categorification, namely there should exist a homological invariant of a three manifold such that you take this gradatory characteristic or some dimensions of these homology groups with certain coefficients and just recover the quantum group invariant. So that's first problem that was motivation for this work I'm trying to summarize today. And in this talk, I'll focus on the simplest kind of quantum group invariants. Well, I'll mention maybe several kinds, but the underlying group will always be SU2. If we talk about Chern-Simons theory, usually things are labeled by compact group, or at the level of quantum group or Lie algebra, it will be SL2. Either way, we'll talk just about rank 1 case, the simplest possible case. Anyway, in this case, the invariants, the so-called Witten-Reshetikhin-Turaev invariants, are exactly the right analogs of John's polynomial and so on. But the first problem is that these are not invariants where you have integrality inside, at least not manifestly. So these invariants depend on a choice of three manifold. So they are invariants after all. And they also depend on choice of integer k, which is called the level in representation theory. So for each choice of k, you get a number, but unlike John's polynomial, Humphrey polynomial, Alexander polynomial, there is no obvious way to extract integer coefficients from anything. So it's not exactly clear what you mean or should mean by categorification. So that's the first problem, and that's the major problem that was an obstacle for a couple of decades, and I want to spend a little bit of time on it. From the viewpoint of quantum groups, the invariants of Witten, Reshetikhin, and Turaev are associated to quantum group at the root of unity. So k in this case appears as order of the root of unity. This little k is the integer. And here I give you an example of WRT, or Witten-Reshetikhin-Turaev invariant for a simple class of three manifolds. We're just starting as far as topology goes, but already for this simple class, you see that k appears in several different ways. So first it appears inside the sign function. And that's actually not so bad, because if you want to write your result in terms of q, which is exponential of 2 pi I over k, then sign can be conveniently written as q to the half minus q to the minus half. So that's fine. It's a nice function of q. This doesn't look so bad. But then you see appearance of k first in front and some power g, which probably gives away which class of three manifolds I'm considering. And secondly, it appears as upper limit of the sum. So if I want to write the answer as some kind of polynomial or maybe function of q, just like John's polynomial or Humphrey polynomial or Alexander polynomial, then I'm basically replacing k by inverse log of q. And if I naively do this in this expression, then I get rubbish. I definitely don't get a polynomial with integer coefficients. I don't get anything with integer coefficients. So therefore, the first problem from this perspective is how do we deal with categorification of Witten-Richter-Hintarive invariants or other quantum group invariants, namely where are these integers that Sir Michael and many others were asking about. So what are we supposed to represent as graded sums of homology groups? So that's the challenge. There are several ways to deal with this challenge or try to approach it. One is to state the root of unity and work there without moving away from Q, which is a root of unity. And that's one approach. But in today's talk, I'm not going to say much about it, probably. Another possibility is to imagine that there is a function, maybe holomorphic or meromorphic function, say inside the unit disk in the Q plane, such that as you approach roots of unity, approaches the desired values of Witten-Richter-Hintarive or other quantum group invariants. So this is roughly speaking what happened with John's polynomial and other quantum group invariants of knots, where you can imagine that they start life at the root of unity, but then since they're polynomials in Q, you can easily see that they are nicely defined inside the unit disk. So there are several developments going back to late 90s and early 2000s, which suggested that something like this might be true. They're based on study of quantum groups at generic Q and so-called SL2C Chern-Simons theory with a group other than SU2, which leads to a Witten-Richter-Hintarive invariance for non-compact group SL2C, the complexification of SU2, you naturally find that analog of level K is a complex number. So that also suggests you should be able to move inside inside this unit disk in the Q plane. So starting back then, there was a natural chase of such functions, f of q, which roughly speaking try to extend the quantum group invariance at roots of unity inside the unit disk. So I myself had a project with Kumaran Vafa and Don Zagir and various other authors either joined us during a whole decade of study or decouple, but this was a very difficult process, in part because looking for such function is challenging, and you want to preserve or keep many properties. For example, it better be invariant of a three manifold. Also, you want to have integer coefficients, and without any kind of guiding principle, one is basically left at guessing that answer, and that's not very productive because there are many versions you can guess. For instance, one of my favorite examples is manifold, three manifold, which is very simple, S1 cross S2, and its quantum group invariants, the WRT invariants at the roots of unity are all equal to 1. So the most naive function f of q, which has this property that as q goes to roots of unity, it approaches 1, is just f of q equals 1. So that's one easy guess. But we can keep guessing, and in fact, we can take Dedekind eta function and take its power, in fact, any power, and adding that to 1 won't change the result because Dedekind eta function vanishes at all primitive roots of unity. More generally, we can take cusp modular form, which also has the same property. And if we're adding these powers of eta function, or more generally, cusp modular forms with integer coefficients, we'll get lots of interesting Q series such that they have the property that they approach expected WRT invariance, in this example, equal to 1 at all roots of unity. So guessing clearly doesn't work. Also, various candidates, which naturally came from the study of knots and this SL2C Chern-Simons theory and various other versions, which I'm not going to describe in detail, produced something that usually works, for example, for knot complements, but didn't behave nicely under cutting and gluing, so therefore did not really form topological quantum field theory TQFT. And this was quite a struggle, I have to say. So since roughly late 90s till for the first decade in early 2000s, this was a challenge. But then a surprise came about, which immediately resolved many of these issues. And the surprise was that we shouldn't be looking for a single function of Q, this holomorphic or meromorphic function, but rather several of them, labeled by either elements of the first homology of the three-manifold, or as was realized a bit later, in fact, first was strongly advocated in our paper with Manolescu, by spin C structures on a three-manifold. So this was quite a surprise, because it was not expected originally during this search, neither from perspective of quantum groups at generic Q, nor from SL2C Chern-Simons theory. The expectations were just of a single series in Q. But once you accept the fact that there should be multiple such Q series for a single three-manifold labeled by spin C structures, then life simplifies, and explaining that is basically the goal of this talk. So this invariance that will be denoted Z hat has to do with some historical reasons, because originally there were various other invariants introduced without hat. As I said, this was arduous process and several various attempts were made along the way, and some modification in the end led to this hat. So they're called Z hat. These are meant to be graded dimensions of vector spaces, homological invariants of three manifolds, which also are labeled by spin C structures. So in this way, the story is quite parallel, as expected to be quite parallel to categorification of knot invariants that we see for the Jones polynomial, Alexander polynomial, and various other invariants. And this label B that labels different spin C structures actually makes sense, at least a posteriori, because there are various other homological invariants of three manifolds which have the same property. For example, Higuert-Floer homology of Osve-Szabo, or equivalently monopole Floer homology that comes from Seiberg-Witten theory. They have similar properties. So in retrospect, it shouldn't be too surprising to expect such invariants labeled by spin C structures. And if you want to recover WRT invariants, which again are functions of a three manifold and the choice of integer k called the level, then indeed you should do pretty much what we expected, namely take this Q series invariance and take the limit where Q approaches a root of unity. But in addition, since now we have invariants labeled by choice of B spin C structures, we should sum over the spin C structures with certain universal simple coefficients. So in that way, you can keep in mind this picture where quantum group invariants are like molecules built of some more elementary entities. These are this Q series invariants that I'll try to tell you about. Any questions so far? Again, feel free to interrupt me at any point.
Yeah, you can unmute yourself if you want to ask a question, or if you want it to ask somebody else in the room, you can just use the chat.
All right. So here is some some examples. So if you're interested in homologies here, then basically this paradigm shift doesn't change anything for you. You should still expect a single Q series, and I'll give you examples in a moment, such that as Q approaches roots of unity, you get desired quantum group invariance. However, if your manifold is not homology sphere, such as, for example, integral surgery on a knot K, then you should expect as many such Q series, and this label B takes values in ZP for P surgery. If you consider other simple examples, for instance, we had example of S1 cross S2 on a slide a moment ago, then you should expect infinitely many such Q series. And they are not exactly super complicated, but they're not also completely trivial either. So our naive guess where we would just take this function of Q to be 1 is not correct. So it's, at least from this framework, you get something interesting that's supported in several spin C structures for several values of B, but it's not a terribly complicated Q series. Also, if you consider that this example of S1 cross S2 is part of a family, so it belongs to the family of S1 cross a Riemann surface of genus G. In that case, you should expect infinitely many such invariants for a given choice of a manifold labeled by Z to the suitable power by the whole lattice. And of course, S1 cross S2 is also another member of another family where we look at zero surgeries on knots. So in this case, zero surgery on unknot will give you S1 cross S2. So it's on crossroads from several perspectives. And those are also manifolds which have infinitely many spin C structures and therefore infinitely many such Q series. So here is some examples illustrating this. If you look at, say, small surgery on figure 8 knot or another knot, in this case it's figure 8 knot, you get this particular Q series. So I'll tell you how it's computed in a few minutes, but this is what the answer looks like. And it has indeed the expected form. So first of all, there is unique spin C structure, so there is only one Q series to expect. And it has integer powers of Q, integer coefficients, but this integer powers of Q are shifted a little bit. There is this overall factor of Q to the minus half, somewhat analogous to what you see in the Dedekind function. These properties you see in all other examples. So next one is some surgery on a 10 crossing knot. In this case, I look at, say, +5 surgery, and it has first homology, which is Z5. So therefore, we expect to have 5 Q series invariants, and here they are. They again have this property that you get integer powers, integer coefficients, and powers are offset by Q times something fractional. So these are examples of manifolds which have trivial H1, first homology, then the next is cyclic homology, H1, and here are a couple of examples of zero surgeries which have H1 equals integers. In this case, you would expect that there are infinitely many of these labels B that label spin C structures and infinitely many Q series, and indeed all of them are independent and non-trivial. You probably can notice a symmetry between positive and negative values of B. So that's going to be a very general feature that we'll explain later. But aside from that, in this case, you get infinitely many completely unrelated Q series invariants. So this is a brief summary or show a couple of examples what the answer looks like. And this is supposed to be an answer to first problem, namely how can we categorify or represent quantum group invariants as sums of dimensions of some homological invariants. So this is not yet the construction of this homological invariance, but a step toward it, which first recognizes integrality properties inside the quantum group invariance. And again, part of this development, in fact, goes back to that work of Waffa and collaborators. Some of the titles of the papers from those days, in fact, do involve integrality, and that's exactly the kind of structure that they were trying to realize. A particular class of examples, which already started using, involve knots and links. And just like a zero surgery on a knot has infinitely many spin C structures, so is knot complement. So if you consider S3 minus K, K for now is a knot, its first homology is H1 equals Z. And again, naively, you might expect the label B to run over a set of integers. So in that case, a convenient bookkeeping device is to take all those invariants labeled by spin C structures and introduce a dummy variable X and arrange all of this in some kind of generating function so that you sum over B inside in integers, X to the B, and coefficient of X to the B is exactly this invariant and spin C structure B. Okay, so that's analogous to what I showed on the previous slide for zero surgeries. Here the story is actually a little bit more complicated in details. I'm oversimplifying it a little bit for the sake of presentation. One has to think about relative spin C structures and various other elements that I'm sweeping under the rug. You can find details in paper with Chiprin, but the basic idea is pretty much exactly as I said. You have infinitely many labels B which take values in integers, and therefore you can define this double two variable object fk that's a function of x and q, but I don't really want to think about it as a function of x. Each coefficient of this function is a nice function of q, but its x dependence is not meant to be nice on the x plane. At least there is no reason for it. So x is really just a variable for this generating function of infinitely, to collect infinitely many q series. That's all there is. Now, if you have links with several components, then likewise you have H1 of that link complement being z to the power equal to number of link components. And therefore you can introduce analogous variables and generating function so that there will be a variable xi for each component of the link. And in this example, if you have, say, 9 components, you'll have 9 variables xi, and you'll get a function of a bunch of x's and our q, which has to do with quantum groups at generic q. Now, the reason this knot and link complements are special, and the reason I emphasized or gave you several examples which are based on surgeries, is the following fact, which is famous theorem of Licorice and Wallace, that every connected closed 3-manifold can be built by integral Dane surgery on some link in a 3-sphere. So in other words, the theory of 3-manifolds is indeed closely related to theory of knots and links, except they're decorated by integer coefficients, which represent surgery coefficients for Dane surgeries. And then a further statement due to Rob Kirby is that different ways of building such three manifolds from surgeries on knots and links are related if and only if the corresponding knot and link diagrams are related by what we now call Kirby moves. I'll show you some examples in a little bit. From this perspective, in this way of constructing three manifolds, we think of, for example, three-dimensional torus, not quite as product of three circles, but rather as a surgery on Borromean rings with coefficient 0, 0, 0, or perhaps as a surgery on some other link that's related to it by set of Kirby moves. So that's why I mentioned knot and link complements in some detail, because once you have this invariance, this, for example, two-variable object fk that depends on x, where x keeps track of spin C structures and q, then you can actually perform the gluing procedure and cap it off, namely build a closed three-manifold, which is a surgery on that knot. And not surprisingly, the invariant for surgery is expressed in terms of invariant of the knot complement. So here at the top of the slide, I show detailed surgery formula for that procedure. In fact, it's a special case of more general surgery description from, again, paper with Chyprian. Don't pay much attention to details of this formula. There is one particular aspect that I'll try to explain later in the talk, but at the moment, I just want you to keep in mind that once you have this invariant for knot complement, or more generally link complement, you can then produce from it invariant of surgery, as illustrated here in the bottom of the slide for surgeries on trefoil knot and figure-8 knot. So in this simple example, they give the same coefficient. This is a particular Brie-Scorn sphere that can be constructed as a +1 surgery on figure-8 knot and -1 surgery on a trefoil knot. So this two ways of constructing it start and use different input data, namely they use invariants of complements of the trefoil knot and figure-8 knot respectively as a start, but then produce exactly the same Q-series, illustrating that different ways of building three manifolds which are equivalent indeed are indeed give you the same answer if the three manifold is the same. So this was for surgery on a single component link. If your link has multiple components, then remember we introduced multiple variables xi, which keep track of spin C structures, and basically number of them is the same as the Betti number, and it can be fairly large for a link with many components. So then there is analogous surgery formula which allows you to build invariant of a closed three manifold by surgery procedure by closing off this toral boundaries with solid tori. And the basic idea is that you have to integrate over this variables that you introduce. So these variables xi that we introduce get integrated out, and you're left with just a series in variable q, which is, again, the general feature here. One interesting fact, just like with the previous formula I showed, is that every time you have a link component, you're actually integrating over x, but also have a summation over integers. So you can say that each xi is accompanied by the corresponding sum over integers. Here on the slide, I have illustration of this general principle, this general surgery for links which are made of unknots. They give you plumbed three manifolds. Basically, you replace as usual, each link component by node when they're linked to connected by an edge. And in this class of 3 manifolds, there is an easy way to produce this integral by associating some universal weights that you're trying, or part of the integrand, to each vertex and each edge. And a theorem says that the result is actually invariant under Kirby moves. And there are moves that in this particular case are sometimes called Neumann moves that change the diagram but don't change the resulting 3 manifold. So any questions?
What does one know about the convergence of these series?
Right, so physics tells you that they should converge inside a unit disk in the Q plane, and except for finitely many singular points, but not much is known about the structure of the singular points. It seems that there is something interesting going on, but again, they haven't really been being studied. Yeah.
I see. And the other question is, you wrote at the beginning that the Witten-Reschdicken-Turev invariant is supposed to be a sum over all b's of these other terms, but there were some dots in front for the factors. What sort of things are they? What are the coefficients?
Right. So the coefficients are some simple objects. Sometimes when I give talks, I write them explicitly, but I realize they sometimes clutter the slides. So I apologize, I omitted them for sake of presentation in this talk, but they're actually quite intriguing. So they turn out to be S-matrix elements for logarithmic or non-semi-simple tensor categories or vertex algebras. This is another subject that we're coming to next. So when this happens, I mean, they are quite simple and explicit, but why they happen to coincide with something logarithmic was a big surprise originally.
Thank you.
Right. In fact, this is exactly the next problem or motivation that I want to introduce. In the study, so I promised you in the title, logarithmic invariance of knots and Q-series invariance of 3 manifolds, and so far I mostly talked about Q-series invariance of 3 manifolds. So let's talk a little bit about logarithmic invariance of knots. And these are based on non-semi-simple tensor categories or logarithmic vertex algebras. That's why the name logarithmic is quite natural. It's many people use it almost synonymously to non-semi-simple. And the problem here, the motivation, is to build a bridge between this somewhat esoteric logarithmic invariants, I'll tell you a little bit about them in a second, and more traditional quantum group invariants, such as all the invariants that I mentioned so far, namely the Jones polynomial, the Homfley polynomial, the Witten-Reschdicken-Turev invariants, are examples of semi-simple invariants because they're based on semi-simple tensor categories, which are usual standard tensor categories. There is nothing exotic, and they have connection to rational conformal field theories. So these two groups of invariants, even in the case of knots, seem to belong to different camps, as illustrated here by the figure. Namely, both have very long history, but one problem in this field, and this is my problem number 2, which is main motivation, is to bridge them. Because there were very, very few connections, very little known how to go from one to the other. So the problem was to build bridges and roads. In fact, the more the merrier. And that was also another big challenge going back to early 90s when such invariants were first introduced. So one of the maybe not the very first, but one of the first kind of invariants of this type, namely the logarithmic or non-semisimple type, is a set of polynomial invariants introduced by Akutsu, Deguchi, and Otsky. These are called ADO polynomials, and I'll show you examples in a little bit. And they really look very similar to John's polynomial, so they're or Alexander polynomial. In fact, there are sometimes called colored or various versions of Alexander polynomial because they include Alexander polynomial as a special case. And these are some of the first invariants of this logarithmic or non-semisimple type. In fact, it's interesting that this paper was published in the first volume of the Journal of Knot Theory and its Ramifications, which started also in its existence in early 90s. And you can see here that indeed this paper is published in volume 1. And now we have several dozen volumes. I don't remember which volume we're on. So it has very long history. I mean, this set of invariants and then the subject. So it goes back to early 90s at least. It's been at least 30 years. But like I mentioned, one of the challenges was that these invariants were kind of outliers. There were several people who worked on them, so you can say they were terribly unpopular, but they were definitely not as popular as John's polynomial or WRT invariants. And it would be very nice to connect them, build this bridge and understand their relation. So in the first part of the talk, I told you more about WRT type invariants and various Q series, which seem to have this semi-simple flavor because I never mentioned anything logarithmic, or I didn't talk about this ADO invariants, but surprisingly, this first part of the talk will actually make this bridge and will cross over to such ADO polynomial invariants. But before I get there, let me say a few words about the history of this logarithmic invariance. So one of the people who worked very consistently on this invariance was Jun Murakami, and he's mentioned here in the original ADO paper for his closely related work on the subject in early 90s. Then a decade later, he wrote many papers on this invariance, but the one I want to show here, roughly a decade later, is on quantum group interpretation of this invariance. So here he says that he works on new invariants of links introduced in reference 1, and reference 1 is precisely the ADO paper shown on the previous slide. And he suggests that here in this paper, we're going to reconstruct this invariance, give another equivalent definition based on quantum groups at even roots of unity. In the world of quantum groups, for SL2, even and odd roots of unity behave rather differently. So representation theory is quite a bit different. So here he picks even root of unity of even order. And the order is related to which particular ADO polynomial he's going to get. And then he works with a particular version of a quantum group, which does not have a semi-simple representation theory. So that's exactly this non-semi-simple type of definition in the world of quantum group, which many people these days call logarithmic. It perhaps shouldn't be confused with logarithmic knot invariants that Murakami and Nagatomo introduced a bit later in a more narrow sense. Here by logarithmic, I mean something that has to do with non-semi-simple tensor categories, which is another, again, fairly standard use for this term. So here are some examples of this ADO invariants for trefoil knot and figure 8 knot. There are polynomials in single variable single variable x, sorry, which actually has the same meaning as x that we used before in this talk. And for each even root of unity, they get a polynomial. And here I list several first examples. And you can see that the very first example, of course, is trivial. You get polynomial equal to 1, but the first non-trivial one is actually just Alexander polynomial up to some simple change of variables. So in that sense, this ADO invariants are generalizations of Alexander polynomial. Now, as already alluded to earlier, there is a connection to the story in problem 1 that we were trying to solve. Namely, you look at this two-variable object that depends on x and q, and you look at it for knot complements for each given knot k. And if you take the limit where q goes to root of unity, then you recover precisely this ADO polynomial invariance as a function of remaining variable x. So in this process, you start with a two-variable object, you take a limit where q goes to root of unity, and the second variable, which is not touched, the variable x, becomes the variable of the ADO polynomial invariance. So in that sense, this two-variable object can serve as a bridge between logarithmic and semi-simple form of life. Here on the slide, I illustrate several other properties, namely this two-variable object is annihilated by quantum A polynomial that usually gives very useful recursive relations to actually find it in practice. If q goes to 1, its limit is inverse Alexander polynomial. This property can be viewed as the simplest of these relations to ADO invariance. After all, we saw that Alexander polynomial is simplest non-trivial ADO polynomial, and so on. So there are several other properties, and you can use either some of them or various combinations to find this two-variable object. So now the list of properties I gave you is in fact more than sufficient to do it for every single example. And this is where in practice examples that I showed you earlier come from. So many of the surgeries on knots and links were obtained by first constructing this function, or again, I shouldn't call it function, this two-variable object that depends on x and q, and then applying the surgery formulae. So another way of constructing it was recently suggested by my student Sang-Hyuk Park. So this is based on quantum group at generic Q and Verma modules, which have general complex weights, again, something that we suspected from the very beginning. And some of the examples I showed you are based on, again, computations for knot complements that come from this R matrix approach. I'm not going to say much more about it, but it basically illustrates the expectation that this Q-series invariance associated with quantum groups at generic Q. Any questions?
I'm reminded of the Melvin-Morton-Rosansky conjecture when you wrote the 1 over delta. Is there some deeper connection with other terms here? I mean, if you expand in Q to the color.
Yes, thank you.
Yes?
You're absolutely right. In fact, it's not an accident, and right. In view of time, I just barely mentioned it and didn't say much about expansion in terms of Vasiliev invariance represented by this pink region here. But yes, indeed, conjecturally, this two-variable object is, for every knot k, is expected to have exactly the same asymptotics as what we see in Melvin-Morton-Rosansky conjecture. So this gives another handle on what this object is, how to compute it, construct it. So basically, one can take this MMR type expansion near q equals 1 in this region, and then the goal is to resum this into an object that depends on q, namely which has natural expansion point q equals 0.
Thank you.
Yeah, so there is a technology to do it. it's called resurgent analysis, which basically goal of resurgent analysis is to transfer domain where function is defined from one region to another region. That's exactly what we need here. And this is how some of the early examples of these two variable objects were constructed. But compared to other methods, it's a pretty laborious method, but fairly systematic. So if one knows the heavy machinery of this resurgent analysis, that gives a way to do it. But you're absolutely right, it's not an accident that inverse Alexander polynomial and in fact the entire Melvin-Morton-Rosansky conjecture appear. All right, so in the remaining part of the talk, I want to come back to the Sergei formula. So like I said before, if you have this way of constructing this invariance for complements of knots and links, and by now we have several different methods. So that's where some of these 10 crossing knots and other examples I showed you come from. Then you can basically build invariance of closed three manifolds by using various Sergei formulae on those knots and links. And the Sergei formulae I showed you, I gave you a couple of examples, all look as some sort of integrals. And I want to explain in the remaining time where these integrals are coming from. So in other words, in this Sergei formula on top of the slide for a single link component, just on a single knot, and below is the formula I showed you for plumbings, which again had analogous structure. They share the same thing in common. Every time you perform a surgery on a toral boundary, you had to integrate over that variable x that was keeping track of spin C structures on a knot or link complement, accompanied by summation over integers n. So you can see, as I highlighted in this slide, that we get the same structure. And that's the only part of the Sergei formula that I want to explain in my remaining time. So in other words, not the integrand. Integrand already essentially comes from the complement of a knot or link and has to do with this logarithmic knot invariance. But now I want to focus on question, why do we get the integral in the first place? In other words, why every time we need to glue two three manifolds in this z-hat territory, in this z-hat framework, we get integrals accompanied by summations over integers. At least for this SL2 invariance, in high rank, there is analogous formula, but you have more integrals and more sums to do. Well, first of all, I want to point out that if we, so we introduced the variables x as variables that keep track of spin C structure. So in fact, this two variable object or multivariable object was already basically Fourier transform of something labeled by integers, namely spin C structures, and x's for dummy variables. So when we try to integrate over x, it's equivalent to say that we're summing over a regional label in this slide called m. So in this way, I want to transform sum over n and integral over x in a double sum over mn, both of which are integers. This is slightly more symmetric form. But either way is fine. Basically, you can declare that every time you glue two manifolds, three manifolds over toral boundaries in this framework, you get either summation over two integers, m comma n, or you integrate over C star variable x and sum over n. So that's the upshot. That's what we have seen. So where does it come from? Well, I actually also showed you analogous Sergei formula or sums for width and Reshetikhin to Rive invariants. So I gave you an example earlier in this talk where we saw that WRT invariant itself is a sum over n, which runs from 1 up to roughly the level. So that's in fact the structure of gluing along toral boundaries or doing surgeries in WRT theory. Namely, every time you have two three manifolds with toral boundaries and you try to glue them, you would encounter analogous sum which runs up to over integers that runs up to k. So more generally, if you work with Witten-Reshetikhin-Turaev invariants for general group G, the sum over Hilbert space associated to a toral boundary runs over weight lattice of your Lie algebra divided by rescaled root lattice by the level k. And then there is also Weil group symmetry, which by which we divide. So that's not terribly important. What is important is that it's a finite set. And for SL2, both root and weight lattices are one-dimensional. So that's why you get summation range over integers from 1 up to roughly k. So in comparison, in this land of Z hat Q series invariants, what we get is 2 copies of the lattice, and there is no truncation by k. The fact that we have no truncation by k is natural because if you work a generic Q, there is no analog of k. I mean, k just disappears, so that's not a big surprise. But the fact that we have 2 copies of the lattice is a surprise. And again, for SL2, lattices are one-dimensional, so that's where the sums over 2 integers are coming from. So why is that the case? Well, the theory of this Hilbert space for WRT invariants can be represented as a space of sections of a line bundle over space of flat G connections on a Riemann surface sigma. So the space of flat G connections on a Riemann surface sigma is a nice symplectic manifold. In fact, it's Keller, and it has a symplectic structure, which often is called a T-bot symplectic form. So you can consider quantization of the space if you have a symplectic manifold that basically cries out to be a phase space for a quantum mechanical problem. And in this case, it's moreover Keller, so quantization can be made mathematically rigorous by considering a line bundle whose curvature is k times omega and taking sections of that line bundle. So the Hilbert space that I showed you on a previous slide for torus, and more generally for any Riemann surface sigma of a genus G, which is space over which we're supposed to sum, in the case of WRT invariants, can be understood as space of sections of some line bundle over space of flat connections on a Riemann surface sigma. Now, I advertised in the very beginning that in the context of SL2 Chern-Simons theory, the level k is gone, and that's where we get, roughly speaking, generic Q. So indeed, what I want to explain next is that the Hilbert space associated to Riemann surface sigma in this context is likewise quantization of space of flat connections on sigma, but for the complex gauge group GC. It's a nice symplectic manifold. In fact, it's holomorphic symplectic because we complexified the gauge group. And many holomorphic symplectic manifolds are actually hyperkeller, and that's indeed the case for this space as well. So it carries a lot of useful structure. Now, the theorem of Narasimhan and Seshadri says that space of flat G connections on a Riemann surface is the same as space of holomorphic G bundles over that Riemann surface. And we can compute the number of these holomorphic sections by Hirzebruch Riemann-Roch theorem, which basically takes the Todd class of this space called bond G and the Chern character of that line bundle, and integrating it over this nice compact space, we get the dimension, which is precisely the Verlinde formula. Now, if we choose the group to be complex, naively, this integral will be divergent because the space is non-compact. However, like I mentioned a moment ago, just like space of flat G connections turns out to be a space of G bundles, the space of complex flat connections is the space of Higgs bundles. And this later description allows you to introduce many useful structures and features, For example, it comes equipped with a circle action that gives this infinite dimensional Hilbert space, the space of sections, a natural grading. And you can compute what's called equivariant Verlinde formula, namely graded dimension of this infinite dimensional space, graded by this additional circle symmetry. So what we need is a version of this Hilbert space for SL2C, and one boundary is a torus. So that was the element in this gluing formula, in the surgery formula that I mentioned before. And in this case, again, the answer is infinite dimensional. So if you think about quantization of this phase space, C star cross C star divided by the Weil group, you naturally get infinite dimensional space with bases either labeled by two integers, m comma n, modulo the Weil symmetry, or if you wish, x and n in less symmetric presentation. So there are several ways to understand this. For instance, even if you take the most boring line bundle, and again, here it doesn't actually matter which line bundle you choose, and try to compute, say, the Hilbert series, the space of just holomorphic functions on C star cross C star. They're generated by monomials into C star valued variables. Let's call them x and y. So you get monomials x to the power m, y to the power n, and these furnish a basis for infinite dimensional space and for the Hilbert series. So that's one way to think about it. Another way to think about it is that each C star is cotangent bundle to a circle. And we know that cotangent bundle to a circle is a phase space and quantum mechanical problem, which involves particle moving on a circle. And for particle moving on a circle, the momenta are quantized, and this is precisely another way to see M and N. So just like Verlinde formula arises as quantization of bond G, in the same way you can understand the summation over M and N, or integral over X and summation over N that we saw before as Hilbert space associated to a torus in such SL2C theory. So finally, let me summarize that today I told you about this object or this theory that often goes by the name Z-hat, and it has several interesting dependencies or bells and whistles. First of all, it depends on the choice of three manifold, and here are the key features that if we try to construct these objects via cutting and gluing of more basic ingredients such as knot and link complements, the answer better be independent on the way how we construct it and just depend on the resulting three manifold. That's where invariance under Kirby moves is important. It also depends on variable Q, and I hope I try to motivate that Q can be thought of as parameter of a quantum group, which is assumed to be generic inside the unit disk, or it's associated to Chern-Simons theory with SL2C gauge group. That's another way to think about it. And most importantly, in this talk, I try to emphasize that we get lots of this invariants, as many as number of elements in the first homology of the three manifold. So these are precisely the spin C structures which played an important role. And now you can ask all kinds of questions, namely how these objects, once you know how to construct them and have some examples, how they depend on each of these ingredients. It turns out that dependence on Q is very interesting. So to people who like modularity or connections to vertex algebras, this is a very rich subject. And in many cases, this Q series turns out to be character of logarithmic vertex algebra. So that's another place where logarithmic shows up. And dependence on spin C structures also provides a new handle, namely it allows you to see various other invariants of three manifolds, which are labeled by spin C structures or spin structures. For instance, you can reconstruct Rochlin invariants labeled by spin structures from this dependence on spin C, and so on. So I think I covered pretty much all I wanted to say, so I'll stop here.
Oh, thank you very much, Sergei. Are there any questions?
Yes, do you have a reference, a paper?
For which part? So there were...
Well, for the whole thing, really.
Well, in the beginning, I gave two references. So one is there's this paper with Cyprian from 2019, and more on logarithmic things is in this joint work down below.
Okay.
Are there any other queries or questions? Well, Sergei, it was very interesting and interesting mathematics coming out there. It's amazing how these things expand.
Yeah, if anyone has thoughts or comments, I would, of course, appreciate it. Feel free to email me.
Yeah. Okay. Well, okay. Well, thanks again, Sergei. And in fact, next week we have Cyprian who's talking. So, so that's very interesting. And he's talking about the applications of search for exotic structures and using Kovanov homology, if I've remembered correctly. So that should be again very interesting. So thank you all for coming, and I guess I will end this meeting now. Yeah.
Thank you all. Thanks a lot.